Well, first of all, I would like to thank Aisha and all the organizing committee for this kind of invitation to the this inaugural first international conference on innovations in chemistry and physics. And as you could actually see from the title, um, is going to be dealing with organometallic and coordination compounds, and of course the applications that these species might actually have in green chemistry, catalysis, and metallic drugs. Um, One of the important things over here is just I wanted to say that I regret very much that I could not actually be as in person present in this conference because I mean your country is also very interesting actually to me. But I hope that the chemistry that I'm going to be presenting today it might actually be of interest to some of you guys, and perhaps eventually this might actually serve as a bridge to have perhaps an interchange, not just in ideas, but also to pay us a visit, a mutual visit to Iran and also to Mexico City. Well, in any case, I mean, this is just so to introduce the talk. Is last year it was the 18th birthday of 18th birth of the 18th anniversary of our institute, and of course, I mean, one of the logos that it was produced on this occasion, it was this, and the representation of this molecule actually means a lot to the institute because it represents the beginnings of the institute was dealing or was related with natural product chemistry, which is going to cover some relevance at the end of this talk. First, I wanted to thank to my students, which are actually the power force that actually move most of the chemistry that you're going to be seeing today. And of course, without them, I mean, I would actually have pretty much nothing to be presenting like I'm going to be doing in this talk. We have to be also very thankful to the financial funding or organizations that actually provide the money to for us to actually just provide not just for scholarship for the students, but also the money to provide for all the chemicals and everything else on the infrastructure to actually produce the chemistry that are going to be presented today. First, I wanted to say that I mean, although the chemistry actually is going to be going around into coordination and organometallic chemistry, we wanted to do this campus not just for the sake of making new species. I mean, of course, just making new species, it might actually be interesting for us. However, we wanted to get the funding. I mean, most of the times these compounds, they have to have some application. And of course, I mean, we have found three different kind of niches where we could actually use these compounds for actually to make some interesting materials or smart materials that I'm going to show some of the applications later on. But in this case, the illustration that we have is to work as a chemosensor for different kind of substrates. In this other case, I mean, we use these compounds as homogeneous catalyst, and of course, I mean, some of these compounds eventually we wanted to, as they work really well, we wanted to support them in such a way that we can actually produce compounds which might be more competitive, particularly in the heterogeneous catalysis field. And the other thing that we do is this medicinal chemistry part, where we use some of these compounds actually to explore. Actually, for most of them, we can actually explore the capabilities of these species to serve as, let's say, for different kind of situations, different kind of sickness, or different kind of illness. Like, for instance, one of them is cancer, and the other one, of course, some of the some endemic illnesses that, for instance, we have over here in Mexico, in the south of Mexico, that is called the Chagas disease. So I'm going to be taking these points a little bit further. I mean, as you could actually see, I mean, probably you would actually say, what is the relation? Or there is no relationship between the catalysis or the synthesis of different organometallic compounds and their use also in medicinal chemistry or as metallodrugs, for instance. But as you could actually see here, this is a very nice representation of the interface, which is actually very thin. So you can actually be traveling or moving from one place to another without any problem. Of course, we know that, for instance, we can use ruthenium, rhodium, or some palladium compounds to do cross-coupling, to do hydrogenations, and of course to do CH activation and so on. But of course, I mean, you can actually do some other or use some other kind of metal. Like, for instance, more recently, there's been a lot of interest in using earth abundant metals, like, for instance, iron, and of course, other compounds like manganese and so on. But of course, I mean, one of the big improvements on this thing is that, of course, we can actually do in the side of the catalyst, we can actually do cheaper catalysts that perhaps it might be more active or more selective for different kind of substances. However, on the other side, if we have ruthenium and we have iron and we have magnesium, of course, these compounds they are not only abundant in the earth crust, but also cheaper. but they are also biocompatible, let's say. Some of these compounds might actually serve very well for the design of some organometallic coordination species for their potential use as metallodrugs. And you could actually see here also that, of course, I mean, we can actually use gold that is being used for a long time for arthritis, for instance, some of these derivatives, some of the zirconium compounds, and titanium species too. Metallocins were used for the treatment of cancer, that we see a little bit more further. However, I mean, you can actually see that most of these compounds, you can actually find it very well in some of the compounds that are used for organic transformations in catalysts. So very basically, what we have here is a representation of an organometallic or a typical organometallic coordination compounds, where you can actually have different degrees of freedom, where the different modifications that we can actually do is, of course, change the metal, and of course, change the ligands, and also change the properties of the ligands. For instance, different kind of ligands that we have is not just, for instance, single ligands like these ones, but we can actually have bidentate ligands or chelating ligands in such a way that we can actually improve the strength of these ligands to keep on the coordination sphere that represents all these parallels here. Of course, for catalysis, it's always desirable to have empty coordination sites in such a way that I can actually use to produce later on some of the first initial transformations to get a catalytic cycle, in such a way that these coordination sites might actually be empty for an ideal catalyst, or it can actually be occupied by a ligand, for instance, in the case of the chelating ligand, such a way that one of the halves of the ligand, it might actually be very well, strongly tied to the metal, and the other one, it might be not as well coordinated, or might not be as, the affinity might be actually lower, in such a way that the ligand might actually coming in and out of the coordination sphere, in such a way that we can actually use it to protect this coordination site, and eventually can actually come and go in such a way that the reaction, it might be produced without any problem. Of course, I mean, some of the other things which is actually very interesting, we've been actually making this kind of chemistry in the later years, is in the use of different pharmacophores. This pharmacophore is actually, it might actually be a natural product, or it might be a molecule that already has a pharmaceutical activity. And this compound might actually serve as a ligand, because also, of course, they have different donor atoms. For instance, many of them, of course, they have sulfur, and other ones, they might have nitrogen, they might have oxygen. And depending on the ligand, it might actually coordinate very well to these metal centers. And then we have a symbiotic relation or a synergic relation between the metal, the biological, potential biological activity of the metal, plus that one of the ligand. So I'm going to start with this story briefly with these kind of compounds. Of course, I mean, my group is actually known in the organometallic and coordination chemistry, because we do a lot of pincer compounds. Pincer compounds, just basically, the traditional definition is a tridentate ligand, and of course, in the center, we have an organometallic carbon metal bond. This is one of the main characteristics of these compounds, because this organometallic bond or this carbon metal bond actually provides a lot of the robustness of these compounds to actually withstand sometimes very harsh conditions. And of course, they actually withstand very high temperatures, which actually allows them to provide the proper energy to activate difficult or hard to activate metals, like for instance, the activation, CH activation, for instance, of sp3 bonds, or carbon fluorine bonds, etc., and so on. But as you can actually see over here, I mean, we have a very nice combination over here, because on one side, we can actually use these molecules, actually the free ligand or even the complexes, actually to see, to explore, for instance, their antimycotic, for instance, the antibacterial activity. For instance, in this case, we only use the free ligands. And of course, what we did, it was changing this aromatic fragment for different fluorinated fragments. And of course, we know that we have fluorine. If we have fluorine, then the activity, the potential biological activity of this compound might actually improve. And of course, that actually provides a lot of other different kind of ligands. And of course, if we study these compounds in solid state, we can actually have very nice arrangements in the solid state to carry on a very nice supramolecular study. Then again, I mean, we can have these ligands, and also because we have already the palladium center over here to study the catalytic activity. For instance, like in this case, we use these compounds to produce these kind of amines, which are actually produced through Harbig-Buchwald complex. So this is a very nice thing on this project. As you could actually see, I mean, we can actually explore different kind of applications for these compounds. I mean, starting from the free ligands, and then again providing the either the coordination of the organometallic compounds. Then we can go into the supramolecular area to make these kind of studies, which is going to be very nice at the end of the talk, because I mean, a lot of these potential supramolecular studies has actually led us to perform some mechanochemical reactions to produce some other interesting compounds, actually to try to reposition some of the old medicines, let's say, that have been used for the treatment of the diabetes type 2. And these compounds, of course, if we create a new phase, then of course we can actually patent it, and of course we can actually explore the activity, and if everything that works, then probably we can actually provide a new pharmaceutical application for this species. So, taking the point of the cytotoxic activity and the potential activity that these compounds may actually have, all this, of course, because we are talking about palladium, this being related to cisplatin. I mean, just very recently was the World Cancer Day, which is a very ugly illness that has been actually widespread around the world, but in the last years, there's been a lot of advances on this area. And of course, these compounds, of course, one of these, I do apologize for this slide, which is in Spanish, but of course, I'm going to make the translation when relevant. Of course, we have the cisplatin, that this compound is probably the king, because all the potential applications that it has, of course, is easy to produce. Of course, it's not that expensive, and however, they have a lot of caveats that we have to consider. Among them, some of the caveats we have is they have a lot of secondary effects like nausea, vomit, diarrhea, neuropathies, alopecia, and so on. A lot of that actually related with the fact that this compound is not very selective for the cancer cells. And then, of course, based on that, I mean, there has been a lot of effort to see its discovery and the application that it might actually have to produce some other species that they have less secondary effects, or even if it was possible actually to produce compounds that doesn't produce secondary effects. And from that, we have two different species. One is the carboplatin, and the other one is the oxalate platin. And of course, I mean, these compounds, they actually have sometimes not better activities, but they are more selective for different kind of cancer cell lines. And of course, I mean, they have different kind of applications around the world. However, in this case, I mean, we wanted to see what we could actually, I mean, for instance, in this compound, I mean, we can actually produce these compounds. What else we can actually to improve this? And as I did show you in the beginning, of course, we can actually change the metal, we can actually change the ligands, or change the same arrangement that you have in terms of the coordination sphere of this compound to see whether we can actually improve the activity of these compounds. One of the approaches that we have, which if you remind the first species that I have, of course, we know that the fluorine has already a pharmacological activity that we can actually have in here. So the inclusion of fluorine, we thought it might actually improve the activity of some of these compounds. In this case, of course, the presence of fluorine might actually bioactivate some of the molecules that we have. Of course, it might actually produce fluorisis, and of course, the metabolism produced, but this is very important in terms of the transportation process that probably we can actually have these compounds to the membrane cell. And of course, the solubility also changes and improves a lot depending on the application that we wanted to do with this species. This is a very simple case, and that's why I wanted to present this first. I mean, this is a very typical compound. Probably you could actually see it's very simple actually to make. We have a phenanthroline over here, and of course, we wanted to use platinum that we know already from the cisplatin that it has already some pharmacological activity. Of course, we are going to put some thiols because I wanted this compound to be robust in such a way that the metal sulfur bond, the sulfur thiols in this case, they are very tightly bonded to the metal in such a way that probably the company is going to keep its identity once it incorporates into the cell. Another things that, for instance, the use of phenanthroline actually brings to the companies, actually might promote intermolecular interactions, and of course, these might actually be pi-pi interactions. The chelate effect of this compound, the fact that it's bidentated actually provides some stability also to the compound. And of course, the fact that I have a nitrogen over here also provides certain stability to these kind of bonds. As I was saying before, I mean, the fact that I have the fluorine over here, of course, provides also the non-covalent interactions. Of course, the presence of fluorine, it might actually provide a better transport to the membrane. And then again, these bonds are actually very strong, as I said. I mean, of course, the fact that I have the platinum, these are going to provide this toxic activity that I'm looking for. And sure enough, some of these compounds, particularly this one, it might be hydrophobic, but of course, the fact that I have the fluorine over here might actually provide amphiphilic properties to the compound. So these compounds were designed, of course, I mean, we designed it to use and to have different kind of or different amount of fluorine. They might have actually in the ortho position, meta or para position, a single fluorine, or we might have actually two different kind of fluorines, or we might have 4 fluorines or 5 fluorines. In this particular case, we just wanted to explore the difference in a single, very subtle difference. The fact that we can actually put 5 fluorines, or we can actually just put 4 fluorines in these positions, such a way that over here we're going to have one proton that in the end it might actually lead to some of the non-covalent interactions in the solid state. This is just going to pass it very quickly because, I mean, of course, with these compounds, the fact that we have the fluorines and the fact that we have different kind of ligands, they are flat. Of course, we can actually promote a lot the non-covalent interactions. And you could actually see over here, we have this pi-pi interaction between the two phenanthroline. And of course, I have the same in this other representation over here, which is actually very nice to try to keep the lattice of this compound in solid state very well stable. In this other case, of course, I mean, as you could actually see here, I only have 2 fluorines, but in this other case, what I have is I have 5 fluorines in this particular case. And in the case of the 5 fluorines, of course, I can have also the pi-pi interaction between the aromatic rings and these fluorinated aromatic rings. The fact that I have also the same over here, you could actually see also in the 5 aromatic rings, I also have these pi-pi interactions too. The same happens with the one I have, the four fluorines, as it occurs in this particular case. One thing that is also interesting is that these interactions might also occur between different kind of rings, as it happens with this ring of the phenanthroline, and in the case of this thiol, where we have the 4 fluorines, or the other one that I have 2 fluorines, that actually also improves a lot the stability in solid state of these compounds. And of course, although I cannot really interpolate these kind of properties in solution, of course, it might actually be predicted or foreseen that some of these interactions might actually be relevant in solution. Once, for instance, if I wanted to use for cytotoxicity, that this company might actually interact with some of the flat fragments that I have in DNA, or to promote these hydrogen bridges also in solution in such a way that that this compound may actually interact as a molecular recognition with some fragments of the DNA. I mean, as I was saying, I mean, I have some hydrogen bonds over here, and those of the phenanthroline in this side, and of course those of the thiol, as it occurs in this position. And then again, I mean, this of course, we might actually occur the same as I have these different substitution. And as you could actually see, the fact that I have a proton over here actually improves a lot, because this interaction doesn't occur with the thiol when I have 5 fluorines. Of course, I mean, then we have 3 compounds over here, and of course, we carried out the cytotoxic activity of these compounds, as you could actually see. I mean, the ones having a better cytotoxic activity, of course, this seems to be this one, which is the less fluorinated one, followed by the one who only has 4 fluorines, while the one who has 5 fluorines, apparently, depending on the kind of cell line, cancer cell line that we are using, it might actually improve or be better in some of the cases. As you could actually see, for in the case of prostate, particularly for the compound 1 and compound 2, the interaction, the activity that we are observing over here is almost of 100%. So, and then if you compare with this one, which are healthy cells, I mean, the activity, this compound is, although it's very active over here, is not very selective in such a way that it actually goes the same way for those which are cancer cells as those for they are not healthy cells. So this is really not that nice. However, for compound 2 is very interesting, because compound 2 has a very nice selectivity for the prostate cancer cell line, but it's very selective for this cell line, but it actually doesn't go that much for those which are healthy. So the same pretty much occurs as it happens with leukemia here on the cell line, the K562, of course, with compound number 3, which actually goes selectively to the 100% of the cells over here. But of course, the selectivity in this particular case, it was actually far more higher, almost 3 times higher than it goes for compound 2. So it seems like this compound, for those particular kind of cell lines, it might actually work better for one particular cell line or another. So in this particular case, I mean, based on the result we got over here on the percentage of cell activity, we actually make the determination of the IC50 values over here for different cell lines, which we consider that they were actually the more viable one. As you could actually see in this particular case, I mean, we are seeing that the best activities that we are observing, of course, is with compound 2 and with compound 3. And then again, in this particular case, we could actually see for these particular cell lines, it goes really well for this one. It was really well actually for this one, but then we always have an activity which is actually more pronounced for the one we have with 5 fluorines. This might actually be related to the transportation phenomenon through which this compound actually penetrates the or to travels to the membrane, and of course reaches the position in such a way that we can actually kill the cell. We may actually some docking experiments, and these docking experiments, as we could actually expect, just predicting from the supramolecular analysis within the solid state, that we might actually have this pi-pi stacking, which is actually a molecular recognition that we might actually have from this compound. And you could actually see this is within the molecule, but over here, I mean, we have some CH-pi interaction. This is something we didn't actually see in the analysis that we did in the supramolecular manner, but of course it was predictable to actually have it because this compounds might actually interact very well, not just with ring by ring in pi-pi interactions, but also other kind of interactions where the pi clouds actually or the pi density over here interacts directly with some protons in the DNA. The same pretty much happens over here, where you could actually see there are different fragments in different segments of the DNA where we could actually have hydrogen bridges, which are also very interesting and very important for this compound to actually carry out the interaction that we have. With this compound is also the fact that we make the DNA interactions experiment in such a way that we could actually see that once we put our compound, the fluorescence of this compound starts to, or this adult actually starts to shoot down. So in such a way that we are seeing some intercalation of this compound. So this conclusion was actually reached based on these results. And of course, I mean, I have to present just to put faces to the names. This and also to see that the beauty is not actually separated from the chemistry or from science. And these girls this actually was the one who actually performed this very nice chemistry. It was only a bachelor's thesis for this case. So this actually was published very recently, actually almost a couple years ago, and in a journal of the specialty which you could actually access. Getting back into the fluorine, of course, this was not the only approach. I mean, as I say, it was a very simple approach, just to put in context of most of the chemistry that we are actually doing. But of course, very recently, and there's been a lot of chemistry related. Well, it's not actually very recent. It's already a number of years that the imidazole and some of its derivatives have been used for different kind of applications in chemistry, particularly that being from catalysis at the fact that we know that already the imidazole fragment has got a lot of potential for bacteriological activity, being used as antihistaminic, anti-ulcer, anti-hypertensive, antifungal, of course, antiparasitic, anti-emetic, anti-cancer activity, which is actually very relevant for what we want to actually do, and antiviral. And of course, I mean, we have two different kind of frames over here. One is going to be the imidazole, and the other one, which is very simple, and they actually behave very similarly, the benzimidazole. And of course, I mean, we actually use the imidazole just to start on this, and we're producing these compounds. We wanted to keep the fluorine, and then of course, but we also wanted to, in a way, to serve as a buffer the other arm of this compound. One was completely, and then one was completely fluorinated, or we can actually modify the amount of fluorine that we wanted to put over here, and the other one remains without fluorine in such a way that we could actually also make the supramolecular ester. And as you could actually see, this compound, this was actually not published in a journal related yet with the biological activity, but in the first instance, these compounds or these ligands were used actually by my colleague Juventino Garcia, also at the UNAM, to do some very nice catalysis experiments. So we use these compounds to produce in situ some heterocyclic carbene derivatives to actually make some hydrogenation reactions. And on the other hand, we use these compounds just to explain actually the supramolecular interactions that they may actually have in the solid state. And this was actually published in Crystal Engineering Communication. As you could actually see, I mean, most of the projects, they have a lot of those where we could actually produce a lot of this chemistry and really publish it, or to put in different fields of interest for different kind of groups around the world. Of course, with the ligands in hand, As you could actually see from this that we have over here, of course, this one example, this was benzene, but of course we can put a methyl, we can put pretty much any R group that you would actually want to put there. And then we actually make the compound, the silver compound, which is very easily because you only use silver oxide, the silver oxide. Then again, we have this already, this is already an NHC carbon, an heterocyclic carbon organometallic species. This by transmetallation reaction will give place to the palladium compounds. And the palladium compounds, you could actually see also the fact that we have the fluorines, and they have very nice interaction in solid state. They produce very nice crystals that allow us to, in a kind of easy manner, to obtain the crystals and also to obtain the crystal structures, as it happens with this silver compound and of course with the palladium derivatives. The palladium derivatives, of course, they've been used for different cross-coupling reactions, including Heck, Suzuki, and so on. And so many of them, they have already been reported over here. Of course, the anti-cancer activity of these species, they have also been examined. And we have recently reviewed this on this nice review in 2021 in Anti-Cancer Agents in Medicinal Chemistry. Of course, the silver compounds, they might actually be also tested as anti-cancer activities. However, silver hasn't been very successful in the treatment or for cytotoxic activity, but they work really well for antibacterial activity. So these compounds, they are actually very robust. And some of them, particularly the one which is totally fluorinated here and here, this compound, it doesn't get very much affected by the sunlight. So which is also a very nice thing to do. And of course, I mean, once you have these compounds, you have the silver compounds, you can actually do the transmetallation with pretty much the transition metal you want. So you can actually produce the platinum, you can produce the rhodium, the ruthenium, pretty much any species you want actually to there. And in this case, we actually use or produce the gold derivatives. In this particular case, as you could actually see, we have the smaller R group that we can actually put here, which is a methyl. And with this, we have carried out two different kind of studies. One, of course, the the cytotoxic activity or the anti-carcinogenic activity on different cell lines, which they work really well. And of course, we here actually make the variation by methyl, by ethyl, propyl, and so on. But these compounds, they actually work very well also for the synthesis of propylylic amines. As you could actually see, this is a two-component reaction where you could actually use catalytic amounts of these compounds, and they produce a very large series of this. I don't remember exactly how many right now, but I think it was some series of 25 different kind of substrates. But then we wanted to approach these kind of compounds, not just to the fact that we have something produced, let's say, synthetically. On the other side, as I was mentioned at the beginning, and to try to make this proper combination with the natural products, we wanted to use something closer to that. And of course, I mean, as I said before, we can actually either change the metal, and this actually is going to change the oxidation state, or we might actually have additional coordination sites. We can actually improve the redox activity, the geometry, and so on. And of course, the change of the ligand, as I said, it might actually change a lot. Mainly speaking, the solubility, or we have a ligand that already has a property, a pharmacological property, we can actually use it to complement that of the metal in such a way that it might actually work in a synergistic manner. So, in making this review, the one I told you, the anti-cancer agents in medicinal chemistry, we came into these kind of schemes in such a way that generally, I mean, we can actually have metallodrops, or we may actually have small molecules or natural products to try to use it in therapy. Of course, I mean, this part of the mechanism, they might be different because this might be more signaling and so on. But of course, the signaling, they might be related to these things. And I said to myself, I mean, why don't we make a combination of these two sides, the metallodrops and also the natural products, and see where we can actually something related with cancer. So in that way, of course, what we have here is probably the use of natural products. And the more simple, I mean, it was actually, the inspiration actually came by just taking a very nice cup of coffee. But you can actually be having some tea, you can have a cup of coffee, or you can actually have some hot chocolate. After that, we can actually have some theophylline for the case of the tea. We can have caffeine in the case of the coffee, and of course we have theobromine, which we can actually have it in the chocolate. So from this, as you could actually see, I mean, we are not moving from the basic frame that we established. I mean, it was imidazole and something which actually resembles a lot the benzimidazole, Of course, I mean, these compounds are more biologically related because they are xanthines. These xanthines, I mean, they might actually produce also some N-heterocyclic carbons. One thing we wanted to do is not to start directly with these compounds. I mean, of course, we wanted to functionalize them. In this case, we have already one, but then to produce the sodium salt to get to the further functionalization, of course, we wanted to functionalize it over here, but we wanted to have another potential center where we can actually either functionalize later on, or even this company might actually coming in and out in a hemilabile to put the hemilabile properties to this kind of ligands. So of course, we made the ligand, and of course, you can actually produce the sodium salt, and after that, you can actually produce the silver compound, which of course, you can actually use this compound for the measurement or for the determination of the antibacterial activity, and then we produce the ruthenium compounds. Of course, this is based on the presence and the antecedents that we have on the NAMI species and so on. That of course the NAMI has been working pretty well, but of course we wanted to see whether with the compounds we have, it might actually work something better. In this particular case, I mean, as you could see, this arm, the hydroxyl over here is not coordinated directly to the metal, but this may actually provide some further properties to the compound. And then we have also this palladium derivative over here. Of course, I mean, what we could actually see is that these compounds, they are very active for certain cell lines, for instance, like in this case for the prostate cancer cell line, and this other one, which is also very interesting, which is cancer, lung cancer, but also which is very interesting for these compounds is that when they go to the healthy cells, they are not really as toxic as it happens to the other cancer cell lines, which is something we really want when you design this kind of species. And then again, we can actually produce a different kind of functionalizations. Of course, I mean, in this case, instead of using a single diol, we use a diol. Is a single alcohol, we use a diol over here. And the diol, it might actually be functionalized with phosphorus, or it might actually just live without the phosphorus and then produce the compound over here to produce similar species to the ones we produced before. But these compounds, once we have it attached to the phosphorus, of course, the compounds tend to be far more stable than the ones I presented before. And of course, these compounds, they are organometallic ones, and these compounds that we have over here, they are coordination ones. And these compounds might actually be used not just for the biological testing, but also to use as a catalyst, for instance, all the palladium and the ruthenium compounds for transfer hydrogenation reactions, while the palladium compounds might actually be used for cross-coupling reactions. This compound actually led us to the production of another compounds. I mean, I have to confess that what we wanted to do over here, it was first to carry out not the synthesis of these compounds exactly. The fact that we have the nitro over here, we wanted to further reduce this to the amine group and then to produce another fragment of imidazole on this side to try to make a Janus species. However, in the process, I mean, we failed to produce this, but we have a lot of these compounds, so we decided to use it. I mean, we make a quick revision into the literature and see that this compound hasn't been produced and synthesized before. So we decided to do this chemistry and to produce the iridium species. I mean, of course, in this case, I mean, iridium, you can actually do a lot of catalysis, CH activation, hydrogen transfer, and so on. But then in this case, this compound actually worked really well for the biological activity, and there has been a lot of interest recently because because this compound is kind of it doesn't really produce or let's say it produces compounds they are very selective for certain kind of cell lines, cancer cell lines. In this particular case, as you could actually see with these two compounds, in the case this of course, I mean, all the results I have presented and this in particular, all they are in comparison with cisplatin. I mean, cisplatin represents this bar over here, but as you could actually see in this particular case for this for breast cancer, the activity that the compounds, these two compounds, is superior, far more superior to the one that cisplatin. And if we compare, for instance, this one over here, complex 2A, this is actually far much better because it's very selective for the breast cancer, but also is very selective, or it doesn't go for the healthy cell lines. So this is actually tell us a lot in which way we can actually be starting improving these compounds. I mean, of course, you could actually see 2B. I mean, probably it's because the transportation, it might actually reach a lot of the interior organs of the cell in such a way that it goes very, very, very highly, not just for the cancer cell line, but also for the healthy cell lines here. And then these compounds also, particularly these ones with the nitro, they actually take us also to another to study another potential use of these compounds, which is the Chagas disease. Chagas disease is something very bad. It's a very bad illness that actually, of course, is a parasitic illness that actually occurs a lot in the south part of Mexico, because the weather actually provides a lot of proper environment for this particular kind of bugs to be developing in a proper manner there. So it's called over here. It's called the kissing bug, and the kissing bug, of course, what it does is related to the bed bug in such a way that it goes and of course it bites and it feeds from the blood, the human blood in particular, and of course in the process, and then once it's completely full, generally it defecates. I mean, it sounds pretty bad, but actually what it does, it defecates on the area, and in such a way, I mean, most of the times, and these eases, these feces of this bed bug actually carried out the parasitic part that actually gets its access to the bloodstream, because I mean regularly when we see this, I mean, produces itchy, and this itchiness actually, well, once you start to scratch it yourself, then actually serves as a model to stream blood. So this actually is being taken a lot of problem and a lot of interest, particularly from developed countries, because this initially was considered as developing countries, but developed countries didn't actually put very much attention to this, because I mean, it was a disease or an illness that it affect them that much. However, the number of cases of Chagas disease has increased a lot, both in Europe and the United States, which actually has actually raised some red alarms for the pharmaceuticals actually to design new compounds. You could actually see this is a kind of forecast of how the market value in Chagas disease medication should actually goes in the next following years. You could actually see, irrespectively of what you see, there is going to be different kind of companies. Probably you will recognize Novartis and Merck, that they are making a lot of stress and a lot of investment to try to see whether how to improve these two, which are the two only medicines or the only two pharmacological ingredients that we have available to go against this Chagas disease. As you could actually see, the inspiration that we actually took is the fact that we could actually have an imidazole and we have a nitro groups, and these two compounds, of course, the difurtimox and the vesnidazole, most of the time they are not completely available actually. Although the Chagas disease is very treatable in the first, in the initial stages, I mean, regularly it happens that the lack of attention or sometimes is the lack of care, even by the people or the health care systems, regularly doesn't get that kind of attention. And of course, this disease actually increases its graveness later on. So, although we tested actually most of the compounds with the metal it was actually far more active, in such a way that it didn't actually work. Because pretty much it goes like when you're playing boliche, for instance, then in a way that these compounds actually they go for everything. So we thought that we could actually use these compounds, but also again, the fact that we have the anionic compounds over here, the azolium salts, they didn't work really well, but they actually serve us a lot to produce this series of compounds, which is a very simple reaction. And these compounds, as you could actually see, I mean, the LC50, they are actually far much better than actually the benznidazole or the nifurtimox in some cases. For instance, in this case, we have 2.72, 1.5, or we can have 3.61 and 1.2. If you compare, for instance, with this compound, which is compound 3G, which is the one who has a lot of more fluorines, which actually turned out to be some of the more active ones. Yes, so this component might actually work really well. And then once again, the presence of fluorines, it might actually serve actually to improve the transportation of the compounds to the cell membrane. So one of the things is sometimes I wanted to change, I mean, because they said, I mean, iridium, platinum, and palladium, they are really expensive. So sometimes we have to move to metals, which are cheaper in a way. So nickel, it might actually be the action. In this case, I'm going to just switching gears once again to catalysis. And one very interesting reaction is the thiolation reaction, or then this thiolation reaction is actually, the reaction is a cross-coupling reaction between thiols or disulfides, with a corresponding halogen benzene to produce the corresponding non-symmetric thioethers. And as you could actually see, this compound actually works like a charm. It works really well. I mean, we produce very high yields in particular cases, and of course, I mean, we have a lot of problems still with heterocycles. Regularly, this is related to the heterocycle reactivity directly with the metal. Sometimes, I mean, these compounds, they actually serve as a chelate ligands, just completely killing the activity of these compounds over here. Well, let me just go a little more faster just to complete this. And of course, I mean, this compound with the same ligands that we used before, but now the totally fluorinated version, at least on the arms, and this compound may actually work for these borrowing reactions in such a way that we can actually produce imines. And then after that, these imines, starting from benzylic alcohol, they actually work really well. I mean, yields are not that much impressive in some cases, but in other ones, they are really, really nice. And of course, we can actually use different kind of compounds, which in the end, I mean, they might actually be very interesting, in particular for the agricultural industry in a way. Here, once again, I mean, we use these compounds. In this case, I mean, we synthesize the nickel derivatives, as you could actually see. The difference on the fact that I don't have the two nitros on this position, I mean, I just strip those nitro from the scheme directly to prove the activity of this compound. And as you could actually see, I mean, particularly for these compounds, I mean, this compound actually seems to be the best, as it has a mixture of the best of two worlds, because we have one arm totally fluorinated and the other one is not. And this compound actually total fluorinated changes a lot in the activity, and of course the other one, it seems very similar to the one over here. So with this compound, who was the more representative one, I mean, we tested with the just with the breast cancer and also with the prostate cancer, and of course we have some very nice results over here, which are very much related, and they are actually far much better than the ones exhibited by the cisplatin. And then just the last one I wanted to mention over here on the use of natural products, let's say, and the combination with metals for the production of different kind of compounds for different kind of applications, is this compound. This is a publication that we published not that long ago, and this was actually with people who actually does very seriously the natural product chemistry, and they are actually able to isolate these two acids, the vigerinoic acid and the carinoic acid. This is my colleagues Mario and of course Gabriela Rodriguez at and a very nice state over here called Michoacan, in the city of Morelia. And of course, I mean, with that, we make this compound. This is the structure of the vigerinoic and carinoic acids. And of course, once you put it in contact with zinc acetate, we can actually produce this kind of small clusters. And these clusters, they have very interesting biological activities, and also they have also very nice catalytic activities, also for the production of biodiesel and some other things related with that. More recently, we have been actually working once again with the carinoic acid, and this carinoic acid may actually work also with ruthenium and these ruthenium compounds, as you could actually expect. I mean, we are waiting still for the results, and but we presume that this compound may actually have a very toxic activity that some of the compounds we have produced before. And of course, as you could actually see, this compound is also again an organometallic species, but this compound might actually give very nice surprises that I will keep you in touch regarding this. One thing which is important in this particular case is that once we get a crystal structure of these compounds, we can actually produce both enantiomers. I mean, they are two different kind of enantiomers produced by the presence of these two different kind of archival centers. So of course, the activity might actually be produced from one of the enantiomers or the other one. And then, of course, I mean, we haven't stopped here. I mean, there is a lot of molecules which are very interesting. And of course, we have compounds that they have an antifungic natural activity, like is the case of the lapachol. It's called lapachol. And this compound, of course, it might actually have a lot of interesting biological activity. One thing which is very interesting is that this compound, you might actually mix it very quickly with here we have ruthenium. And then of course, this compound may actually have to produce your corresponding organometallic species. And this reaction is actually very easy and proceeds very, very simple. And this compound is also some of the chemistry that we have been recently studying. And of course, we wanted to study a little bit more further, not just for the biological activity that we expect that is going to be pretty nice, but because there is a lot of other kind of derivatives that we can actually use. But of course, we can actually use these compounds for catalysis. Then, as I said, there are different kind of secondary metabolites, for instance, that we can actually have from different kind of plants. The thing is, over here, we cannot use extracts. This is all the things that usually happens when I give this talk. People approaches to me and say, well, I have the extracts with different kind of plants, but the thing is, we cannot work with extracts because the extracts are a very complex mixture of different kind of compounds. For this kind of reactions, for this kind of research that we are doing right now, we need actually the compound totally isolated and characterized. So this I could actually present a little bit more about the talk because there is some other things we have been doing, of course, with some compounds which are fluorescent, like these ones that I am showing here in collaboration with my colleague at Institute of Materials also at the National University of Mexico, Ernesto Rivera, which we've been working with these compounds in fluorescence and different kind of optical and phosphooptical properties. Different kind of other things. This is just to make some publicity over here regarding the two books that we have published on chemistry of pincer compounds. You could actually have it, and in the end, there is a lot of ideas, and the contributions that the people has actually done to this area has been a lot. So then, of course, we have another things that I hope I have the time to speak to you in a different opportunity. In the meanwhile, once again, I wanted to thank Aisha, and I wanted to thank all the organizing committee for this very nice conference and the invitation to actually give this talk to you. Thank you very much indeed. If you have any questions, as I said at the beginning, you have my email, which appears actually on the first slide. You can throw me an email, and I will respond to you as soon as I can. Thank you very much indeed.